Hi scholars, today we're going to talk about functions and function notation. Now likely when you first learned about functions, you learned about them sort of as a input-output rule, right? So we could have f of x equals x squared, and really what that's telling me is if you give me an x as an input, my output is going to be that value squared, right? And we certainly learned how to, for example, make function tables. Could be like xy tables or x f of x tables, and if x equals 3, f of x would equal 3 squared, otherwise known as 9, and we could fill those in. Now this is a fine way to start thinking about functions, certainly. However, we can do a little bit more with this notation, and so let's take a look at a couple of examples. Example number 1. Let h of k be the number of subway riders in the BART system in thousands, k days after January 1st. Translate the following expressions into words. Okay, so this is an example of where we can use function notation to actually make sense of a real-world situation. So let's take a look. We are given a function, the function has a name of h. So let's put that in blue. So that's the function name, and the input here is k. So let's put that in red, and this value of k represents the number of days, right? K is the number of days after January 1st. So the input is representing a number of days. So if I look at h of 9 equals 170, this 9 right here is telling me that 9 days after, right, or sorry, January 1st, which would be January 10th, right, otherwise known as January 10th, then something is happening. So what is happening? Well, the function, the output of this function, is telling us the number of subway riders in thousands. So if the output right here is 170, it's telling us that there were 170,000 riders. Okay, so one way to interpret h of 9 equals 170 is on January 10th, there were 170,000 riders. Okay, let's take another look at another example. H of 12 equals h of 10 plus 5. Now this is an example where a function is actually being defined, right? We use our equal sign sort of, this is how we're defining this value, this function value, in terms of another function value, h of 10, right? Well, what does this mean? Well, h of 12 is, right, again, the output, the number of thousands of riders, 12 days after January 1st. So this is representing the number of riders on January 13th. In a similar way, h of 10 is representing the number of riders on 10 days after January 1st is January 11th. And this plus 5, we say, well, is that plus 5 riders? Well, no, it's not, right? So this is actually plus 5,000 people, okay? And the reason why we can interpret this is that all of these values right here, h of 12, this, again, is an output, right? This right here is the number of subway riders in thousands. This is the number of subway riders in thousands. So this thing has also got to be the number of subway riders in thousands. So this is actually representing 5,000 people. So let's interpret this. What we're really saying is that on January 13th, right, there were 5,000 more. So here, on January 13th, there were 5,000 more riders on the BART subway system than there were on January 11th, right? Put differently, we could actually take this whole equation and rewrite it as just as h of 12 minus h of 10 equals 5, right? We can see we can just subtract h of 10 from both sides. And this right here shows you that the difference in subway riders between 12 days after January 1st and 10 days after January 1st is 5,000, right? 5,000 riders. So that's another way of interpreting the same thing. So it's basically saying that there were 5,000 more riders on January 13th than there were on January 11th. Let's take a look at another example. Example number 2. If h of x equals 3x squared plus 1 over x, then what is the value of, and then they give us a few function values to compute, to calculate. So we can interpret this as a function as an input-output. So if you give me an x, what am I going to do with it? I'm going to square it, multiply it by 3, and then add 1 over that same value. So let's use this idea to calculate h of -2 if my input is -2. And it's pretty simple. right? So we just basically, everywhere we see an x, we plug in a negative 2. So this is going to be 3 times negative 2 squared plus 1 over negative 2. And we can calculate this. That's negative 2 squared is 4. 3 times 4 is 12 plus 1 over negative 2. So this is going to end up being 12 minus 2, otherwise known as 10. Oh, sorry, 12 minus. This would be 12 minus 1/2, otherwise known as 23 over 2, or 11 and a half is fine, or 11 and 1/2. Now the same thing that we did with when we had an input that was a number, negative 2, we can do the exact same thing if our input is an expression, right? So here we want to calculate h of negative 2x, and we go about it exactly the same way. And wherever we see an x, we're now plugging in not a value, but an expression, okay? That's allowed by using these function rules. So we're going to say this is going to be equal to 3 times negative 2x quantity, the quantity negative 2x squared, plus 1 over negative 2x. And we can calculate all of that. Negative 2x squared this is actually equal to 4x squared. 3 times 4x squared is 12x squared plus, well, actually we'll just make it a minus 1 over 2x. And we can't really simplify this anymore, so this would be our answer here. And so this is an example of plugging in an expression, finding the function value of an expression as opposed to just a number. And we can do the similar thing, a similar idea with 5x plus 1, right? Now it's fine, that's a binomial, right? It has 2 terms, but it just is basically saying everywhere you see an x, the input now is this binomial 5x plus 1. So let's see what happens when we have a binomial as an input. Well, we're going to have 3 times 5x plus 1 quantity, right, the whole thing, squared, plus 1 over, and again, 5x plus 1. And so we can actually multiply this out if we wanted to, right? 25x squared plus 10x plus 1, multiply all that by 3. So we could simplify this even more if we wanted to, but this is the general idea. Let's take a look at one more example. Example number 3. The graph of the function h of x equals ax squared plus 2x plus 3 is shown on the xy plane on the right. So this is a function. We can graph a function on an xy plane. And the question is, what is the value of a? Okay, so this is a really important idea, concept, when we're dealing with graphs of functions. If this point 4, 3, so we're given this point, right, 4, 3, so let me just write it a little bigger so we can see it. This is the point 4, 3. It means basically that when I have an x value of 4, right, an input of 4, my output is going to be 3, right? A y value of 3. The output is 3. The function value is 3. Another way of saying this is, if x, when x equals 4, my function f of x, that value is going to equal 3. Okay, so we can actually use this information to create a new equation using the equation of this function that is solvable, where we can isolate the value of a. So instead of h of x, oh, here, sorry, I called it f of x over here, but right, this is the function h, we're graphing the function h, so we can name it h of x. So when h of x is 3, so when h of x is 3, okay, I know that that equals, well, it's going to equal ax squared plus 2x plus 3, but I know that x is 4, right? So this is actually going to equal a times x squared, which is 4 squared, right? Because x is 4. So a times 4 squared plus 2 times 4, you get the idea, plus 3. And now we can solve this. Well, that's nice. Look, the 3's already canceled. 2 times 4 is 8. So I can end up with, right, I can subtract 3. Okay, so I can subtract 3 from both sides. I can simplify some stuff. I end up getting 0 equals, 4 squared is 16 times a plus 8. And I can solve that. Subtract 8, divide by 16. I get a equals negative 1/2. And we want to ask ourselves, does this answer make sense? And the answer is, it certainly does make sense, right? Because we know that we wanted to have an a value that was negative because this is a parabola, right? This is a quadratic function. It's concave down. It's a frown, which means that the a value should be negative. So it does make sense. And we could check this, right? We could put in negative 1/2, the value right here, and we could actually plug in. If I put in x, if I calculate h of 4, right? If I plug in h of 4, do I get an answer of 3? And it is true, of course, that when you plug in 4, you end up getting an answer of 3 because we found that value of 1/2 by plugging in those numbers 3 and 4, right? But it's still always a good idea to check your work. All right, have a great week.